Okay, so this is the example example 5-1 in your book. Okay, and we're told there's a load here, this load F on this arm, and so the load is going to cause a torque through the arm. It's also going to cause a shear. It's also going to cause bending moment. Okay, so we have the stresses at 2 points, point A and point B. Okay, so we can take a look at, let's say we don't know exactly where the greatest stress is going to be, but we can take a look at them. So we can look at point A, and at point A, okay, we have a stress element here. And on this stress element, we have this shear stress due to the torque. Okay, and this is our tau xz, and it is equal to TR over J from our shear stress equation from applied torque. We also have a normal stress there as well, which we'll call sigma x, and that's due to the bending stress at point A. Okay, and that is equal to our flexural formula, which is mc over I. Okay, and that's due to the bending here, so we're going to have this axial stress due to bending, and we're going to have that shear stress due to the applied torque. We also have the equal and opposite for those values as well. Okay, so obviously they act on both faces, and the shear is counteracted as well on that face, and that's the tau zx. Okay. Now we can calculate those stresses that point. We also have point B. And at point B, we have these two shear stresses. Okay, so we have the shear stress that's due to the downward load, right? So we have this load, which is also going to act here. So we have that downward load at point B, do that, and we also have that torque. Okay, so that torque is also going to cause your shear stress as well at point B. Okay, so we have these two shears, so we can represent that here. We can say, well, this is the shear due to the load, which is 4 times the shear over 3A for the solid cylinder, and then we have the other shear that's due to the applied torque, which is TR over J. Okay, and the coordinate systems here, we're just saying that this is Y, this is X, and then along the rod is Z. So let's look at point A, and we're told some things about this. The material is a 2024 T4 aluminum. The yield strength is 47,000 psi, and we are also told that in this case the rod length L is equal to 6. We're told that this length A is equal to 8, and these are inches, so 6 inches and 8 inches. And we're told that the load F is 1,000 pounds. We're told the diameter, the outside diameter of the rod, is 1.5 inches. And we say that it's at room temp. Okay. And we're just going to consider these states of stress. So let's just calculate our stresses so we can get our principal stresses. Sigma x for point A is mc over I. Okay, so that's going to be F times L, right? The force times the distance of the arm times the distance to the neutral axis. Okay, there's our moment over I. So if we calculate those values, we get 18,108 psi, 18,108 psi. If we calculate our shear stress, tau xz is the applied torque times the radius over J. So in this case, it's the force times the distance A. Okay, that's our applied torque here from this arm, times R over J. And if we plug those values in, we get that it is 12,072 psi. We can find the max shear stress and principal stresses from our equations. We have a number of them to choose from, so we can say that tau max is equal to the square root of sigma x minus sigma z over 2 squared, quantity squared, plus tau xy squared. If we do that, we find that that's equal to 15,090 psi. And we can calculate our principal stresses. Sigma 1, okay, is just the center of the circle, sigma x plus sigma y over 2, plus the radius, which is tau max, coming from our understanding of Moore's circle, and that is equal to 24,144 psi, which is greater than either one of the individual stresses. So our principal stress is high. Sigma 2 is 0 because we have a plane stress state, and then sigma 3 is going to be our center of the circle, sigma x plus sigma y over 2 minus the radius, which is tau max. So maybe I'll just say tau max. When I say radius, I'm talking about the radius of Moore's circle. And that is equal to minus 6,036 psi. All right, so now I have everything that I need to look at the von Mises effective stress, and we know that this aluminum is ductile material. Okay, so that we can calculate our effective stress, sigma prime, from our von Mises equation that we derived earlier. So we have sigma 1 squared minus sigma 1 times sigma 3 plus sigma 3 squared, quantity square root, and that equals 27,661 psi. Okay, and then the safety factor we'll calculate using the distortion energy theory. Okay, and our safety factor is equal to our yield stress over our von Mises effective stress. Okay, this is the von Mises equation. Okay, so that's 47,000 from our data over the stress that we just calculated over here, over that sigma prime, which is 27,661, and that is equal to 1.7. So based upon these conditions, that's a good safety factor. If we understand everything and it's in a controlled environment, we can be confident that it's going to be okay. Now, if we use the maximum shear stress theory, okay, we say that, well, in the safety factor in this case is 0.5 times our yield strength over tau max. Okay, so this is the other theory that we talked about, and this is the one that is more conservative. Okay, so if we do that, we can plug those values in, and we get that the safety factor is 0.5 times 47,000 divided by tau max, which is 15,090, and our safety factor in this case is 1.6. Okay, so you can see 1.6 is less than 1.7, so this is a more conservative approach. Okay. So this was at point A. So we just looked at point A, we calculated the safety factor of point A. So we could also do the same thing for point B. Okay, so for point B, okay, this is point B, and recall that at point B we had those two shear stresses acting, right? We have the the stress due to the shear, which is 4V over 3A, and we had the stress that's due to the applied torque, TR over J. Okay. So if we calculate that shear, that 4V over 3A, the shear stress is going to be the same throughout, okay, due to the loading, right? So if we have a load on the end here of 1,000, let me change the color here so you can see it a little bit easier. Okay, so if this load here is 1,000, then we know that the shear here, if we were to slice this at any point, we have that 1,000 pounds of shear that's going to show up at this point at point B. Okay. Okay, so in that case we have 4V over 3A, which is 4,000 PSI, or 4,000 pounds over 3A. So we can calculate the area, plug it in, and we get 755 PSI. Then we can add that to the bending, the torsional shear, which we calculated already, and that max shear stress in this case is the sum of them both. Okay, so we have to consider both of the shear from torsion plus this shear from bending, from that bending at the end. Okay, so when we do that, we add those together, we get that it's 12,072 plus our 755 gives us 12,827 PSI in max shear. Okay, so if we use our theories, if we use the max shear stress theory, or if we use the distortion energy theory, we say that the safety factor is SYS over tau max. Okay, that's the yield and shear, so we said that that's 0.577 times our yield stress over tau max. Okay, if we plug those values in for the distortion energy theory, we get that the safety factor is 2.1. If instead we use the max shear stress theory, we say that the safety factor is SYS over tau max. And remember that the max shear stress energy theory says that failure occurs at 0.5 times the yield stress over tau max. And using that theory, we get a safety factor of 1.8. And again, you can see that in both cases, the max shear theory is more conservative. Okay, so this is where you should be. We should be able to take some simple machines. We should be able to look at their loading conditions at different points, see how those loads leads to the different stresses, and then calculate our principal stresses, and then use our principal stresses in our failure criteria to take a look at our safety factor. So this is the workflow that we will use to really look at the safety factor of almost any design. Okay, so make sure you understand all the components of this. If you have any questions, let me know, and remember you can schedule time on my calendar using the link provided. Have a great day.